Hi class, welcome back. Today we're going to discuss optimization problems. In this section, we're going to discuss in particular problems where we're trying to maximize the function. In this case, it could be a volume, a surface area, a distance, etc., etc. So let's not focus on memorizing the problem, but instead we can discuss the approach that we're taking that will help us lead to the solution. And if you guys notice, if we follow these steps, we're going to be able to generate a structure that we can follow for other problems. So the goal will be to apply minimum and maximum problems or concepts to these problems. Now remember that we have found different ways to find minimum and maximum, and when we refer maximum and minimum, we are referring to the absolute max and absolute min. And I want to remind you guys that in the previous section we discussed, not this last previous section, but in the previous sections, we discussed that absolute max and absolute min can be derived by testing the endpoints and the critical numbers. Now you guys will find in this section that there will be cases where the endpoints will not be clear and we have to find them, and that will be a part that requires us to refer back to algebra. And as you guys will see here, a lot of the work that needs to be done here goes back to algebra, and you guys will notice that the calculus part is very minimal. And so I want to reinforce the recommendation that we should be practicing algebra every single day, right? All right, so one of the most common applications of calculus is to determine the minimum and maximum values. So we have this following example. If you guys think about this could be easily a problem where Amazon was trying to solve. So let's say that you have a box and you want to maintain the same, you want to maximize the volume for a particular surface area, meaning the surface area of a box represents the area of a carbon box or the material that you're using to create the box. And let's say you want to maintain the same surface area, which maintains the same cost, but you're able to maximize, the volume. And that's what we're going to be doing in this example. So we're going to maximize the volume. A manufacturer wants to design an open box. So there's an open box having a square surface base, and a surface area of 108 square inches. Quickly remind you guys that surface area is the area outside this square, as shown in the figure here. What dimensions will it produce a box with maximum volume? So dimensions. All right, so the box is three-dimensional, so therefore, and we already defined a few things, right? It's a box, so therefore it has to be a solid. And a solid has defined to be a dimension where it could have this length, this width, and this height. Now these two don't have to be the same in order for us to have a box. But in this example, they specifically said that the base of this box will be the same. So this dimension and this dimension are the same. So that was a given information that will help us elaborate the problem. Now, they didn't say anything about the height, so we cannot assume that the base and the width are the same as the width. So we cannot make assumptions such as that one variable, that one item equals another item. If we don't know, if it's not clarified, then we have to assume that they must be different. Now in the process, they might be the same, but we cannot assume that. All right. Anyway, so we have a base and we have a height, right? Now the goal is to maximize the volume, so that translates to find the absolute max, right? But now we're trying to find the dimensions that will give us an absolute max of a volume. So we want to find what is x and what is h. So those are the unknowns. So we're going to let x be the length and width, height will be h, and the surface area will be s. So let's talk about the surface area. The surface area is the area around the shape, right? It's the surface, the area of the surface, right? The name itself tells you that. So how do we find that? Because if you guys notice, that was given to us. That was 108. Well, let's look at what we have here. So I did sort of a note here. We're gonna add all the area of every face. How many faces does this have? The front, the back, the right, the left, and the bottom. There's no top in this case. So if you guys notice, if we're trying to find the surface area, we're finding the area of the faces. So if you notice, there's only one face that is in particular like this, right? Which is the base. So that's the only face that has x times x as an area. So I wrote it down here, x times x. But for the sides, if you guys notice, they happen to be the same, right? The same height, the same width. Same height, same width. Same height, same width. Same height, same width. So if I notice, I can just say, well, the area of this will be x times h, x times h, x times h, x times h. And then I can add them together, and that gives me the surface area. Now I also know that they give us the surface area to be 108, so this will equal 108, right? And I wrote it over here. So we have 108 equals x squared plus 4xh, and then we're gonna try to isolate h for a reason that I'm gonna explain in a second. So I hope that kind of makes sense, right? How we found the surface area and why we let that be 108. The reason why we found surface area is because that was given. They gave us something about surface area, so it was motivated for us to know what does that mean in terms of x and h. Now, the actual problem here has to do with volume, right? That's what we're trying to maximize. So that's what we're going to try to do the derivative from, the volume, right? Because you're trying to maximize it. Now, I hope that that's kind of clear, right? The surface area was just an equation that will help us know something about these unknowns. So when I describe the volume of this, and let me see if I can rewrite this as volume. All right, so we have the volume by definition is the base times the width times the height. We know that base is x, the width is x, and the height is h. So therefore, the volume is equivalent to x squared times h. Now, we're trying to maximize this, right? We're trying to maximize this. In other words, we're trying to find the absolute max of this. But in this case, do you guys notice that we have two unknowns, x and h? So it is very common, and actually we are highly recommending that we rewrite the entire volume in terms of one variable. Now you can choose to have it in terms of h, or you have the option to have this in terms of x, or you can manipulate this so it depends on a different variable. But in this case, those are only two variables that we have. So what we're going to do is we're going to use the other equation that was given. That's why this was so important. And try to rewrite, solve for one of the variables. That way, we can use that equation or expression in this formula. So that's what we did with the surface area. We subtracted x squared, and then we divided by 4x. Once h is isolated, we replace h with that expression, and there you go. Notice that the volume is now in terms of one variable. So now this is great, because now our motivation is to find what values of x will make the volume be its maximum. So what are we gonna do? We're gonna find the absolute max of this, right? So do you guys remember that in the absolute max, we do this by finding the critical numbers and using the endpoints, and we plug it into the original function, which in this case will be the volume, and then we just see which one is the highest, which one is the greatest volume. So we're gonna first find the derivative of this, and I did this by multiplying x, simplifying this with this x and this x, and then I distribute the x, the remaining x here, and I factor the 1/4 because the 1/4 is not gonna, it's just a constant, and it probably is just gonna save you more time if I do that. So if I take the derivative of this now, because it's more simple, the derivative of this will be 108 minus 3x squared. And then what we're gonna do is we're gonna find the critical numbers by setting this equal to 0, and then finding whenever this is undefined. Now this is not going to happen because this is a polynomial, so therefore there's nothing that's going to be undefined. Also, I want to make a note here. Let me go back to the top. Notice that once we define our function v, we should probably write something about our domain. And if you notice, this function depends on x, so we should find some boundaries for x. We know that x is it's a length, so therefore the x needs to be greater than 0. It doesn't make sense to have a negative number, right? So we agree that this x has to be positive, a positive value. And then the next part will be for us to determine if there's any lower and any upper boundary. And so now it doesn't really make sense too much for us to have a length that is equal to 0. So we can argue that it doesn't really give us purpose here if we have x equals 0. And so so our critical numbers and our test numbers will probably be there, right? But in reality, it doesn't really make sense, right, to have x equals 0. But anyways, there's another one that we wanna consider. What is the upper bound for x? And the upper bound for x can be found by looking at the actual volume. So let me show you guys this. Let me write a few notes up here. There's two ways we can do this. Let me write it over here. Let me have, this is x equals 0. Has to be greater or equal to 0. So another thing that we have to consider is the fact that volume needs to be greater or equal to 0. The volume, right? So if you guys notice, the volume it's right here. And so if the volume is 1/4 times 108 x minus x squared, that means that this, if I factor the x, we're left with 108 minus x squared. Now this is the volume, and the volume needs to be greater than 0 or equal to 0, right? Now, in order for this to be greater or equal to 0, these two need to have the same sign, meaning if this is negative, this whole thing needs to be negative, so when you multiply them, it gives you positive. But if you guys notice, or be positive and positive, but if you notice, x has to be positive, so therefore this needs to be positive. So therefore, in order for this to be positive, we have to make sure that this is positive. And thus, the only way that this is going to be positive is whenever x is less than 108. The square root of 108, right? So when you plug it in here, you square it, it becomes 108, and that will give you 0, but never negative. So what we're saying here is x needs to be less than or equal to square root of 108. All right. Anyway, so we found those endpoints. Those are endpoints. And now we're gonna find the critical number, right? So the critical number will be found by setting this equal to 0 and solving for x. And we did that right here. We did that right there. And we solve for x by adding 3x squared on both sides of the equation, then dividing by 3. And now we got x squared equals 36. This will give us x equals plus or minus square root of 36. Now we know that x has to be greater than 0, so x cannot be equal to 6. So the critical point is just going to be 6. Now the endpoints that we had so far that we discussed already was x equals 8 and x equals 1 square root of 108. So all we gotta do is take the volume and then just test the values. So test it with x equals 0, and the volume will be 0. Test it with x equals 6, and the volume will be 108. Test it with square root of 108, and the value will be square root of 108. So we can see here that the highest volume that we're gonna get will be whenever we have x equals 6. And thus what we're gonna use here is that we have found the maximum volume with dimensions width of 6, length of 6, and height of 3. We found the height of 3 by just plugging in 6 in here, and that will give us 6. You plug in 6 in here, and that gives us 3 there. All right, anyways, so I hope you guys found this helpful, right? We found the dimensions, and that was a question for us to find, right? What dimensions will give us maximum value? So I hope that kind of makes sense, and so I'll give you guys now some of the guidelines that we're gonna be following, right? So identify what's given in the problem, and all the quantities that needs to be determined. If possible, make a sketch. A lot of times the sketch will be helpful because it sort of summarizes all the information that you're given into one single page, single problem. Write the primary equation for the quantity that is to be maximized. So identify the equation that you need to maximize or minimize. This requires a lot of work because we need to remember our formulas from geometry, trigonometry, trig, and algebra. So reduce the primary equation to one single variable, and like I said, right, you gotta reduce the primary equation to one single variable. This may involve the use of secondary equations that usually are given relating to the independent variable and the primary equation. Determine the feasible domain of the primary equation, that is, determine the values for which the stated problem makes sense. So the boundaries, and then determine the desired maximum or minimum value by the calculus techniques used in 3.1 all the way to 3.4. All right, so here's another example for us to try, and you guys will see how we can use logical arguments to simplify the problem. So in this example, we're asked to find the minimum distance. Find which points on the graph of y equals 4 minus x squared are the closest to the point 0, 2. So we can easily make the picture of this quadratic. We can find the point 0, 2, and then we can think about, like, there must be a point where it's the closest, right? This distance, right? So that point needs to be, that point will be a point on the graph, x and y, and we're trying to figure out this minimum distance from 0, 2. We can argue that this probably be the point where this is going to be perpendicular to the graph, and so we're going to go back and identify now. Since we're trying to minimize the distance will become the primary equation. Now what we're trying to do here is we're going to try to sort of label some points here or use some notation, but we know that the distance formula is given to be equal to the square root of x minus x1 square minus y1 square, right? This was we learned that in college algebra. And so where x1 and x1 and y1 are these points, right? Comes from that point. So x and y were the points on this graph, and we're trying to minimize this, right? So I square that, that went away, so that's square. We square that, and that's how we got y minus 2, and then we can expand this, and that gives us 4 minus x squared minus 2. And what I did here is I replaced, let me just put this here. I replaced y with 4 minus x squared, right? If you guys see that in there, because that was given to us in the problem. That way I can start writing everything in terms of one variable, right? Remember the primary equation needs to be in one variable. So I ended up doing that right there. And then I simplified 4 and a negative 2. That gave me positive 2 minus x squared. I square that, and that gave me this. And then I simplified, and that gave me this. So my distance equation in terms of one variable is given here. It's given right there. So that's what we're trying to minimize. That's our primary equation. So, but here's a little cool argument. If you're trying to, and this works because this is a square root function, and so if we're trying to minimize the distance, right? If we're trying to minimize this distance, and we are only using domain of x where this is greater than 0, what we're saying here is that if you're trying to minimize d, right, the distance, then it will be the same place that when you're trying to minimize this. So using the square root versus not using the square root will not matter in this case, because at the end of the day, you will be the minimum of f of x will be located at the same minimum of the square root, right? So therefore, what we're going to do here, what we're going to do is we're going to focus on this part, and so we're going to try and minimize this, because it will be easier now because it doesn't have the square root, right? I mean, we still try and minimize this, but this is just the same thing, right? It will give us the same critical number, right, than if we were to find it here. So anyways, we'll try do the derivative of this to minimize it. So it'll be 4x cubed minus 6x. Factor out the derivative, and the critical numbers will happen whenever the derivative is 0 or is undefined. And this is going to be 0 or undefined. It's not going to be undefined because this is a polynomial. So therefore, we're only going to get critical numbers whenever the derivative is 0. So since we already factored out, that's nice, because now we can use the zero factor property and suggest that x equals 0 or this factor equals 0. We are going to add 3, divide by 2, then take the square root, by using the square root property, plus or minus the square root of 3 over 2. And these are critical numbers, right? These are the critical numbers. So when x equals 0, or when we have this will give us critical numbers. Now these can give us relative max or relative min. So we're going to use the first derivative test. So let me write it here. First derivative test. Now in this problem, we don't have boundaries, right? We don't have endpoints, because the distance formula can be defined from any value of x. So we won't have boundaries, but what we're going to do here is we're going to look at this graph, the first derivative test. And we notice that we have these critical numbers. Let me highlight them for you to see. These are the critical numbers. These are the critical numbers. And we're going to test every interval between them, right? And when we did that, we chose -2 here for this test. We chose 1, -1 for that test, and we chose 1 for this test, and we chose 2 for this test over here. And so when we did that, we plugged it into the first derivative, right? That's hence the name of the first derivative test. And we got a negative number for the first derivative, we got positive for this first derivative, and we got negative for this first derivative, and positive for this first derivative. So what this suggests is that we have actually a minimizing, right? We're decreasing, followed by horizontal, and then increasing, followed by horizontal, decreasing, followed by horizontal, and then increasing. So pretty much what we have here is something of this form. So like this, like this, like this, like this, right? So we can argue here, if we're trying to minimize this, we know by the fact that the function keeps, increasing as you go to the left side, and it's increasing as you go to the right side. So we know by the fact that there will be no other term, because otherwise we would be able to see it here. So there's no other way where it's decreasing and decreasing. So therefore, this suggests that this must be the absolute min, right? The absolute min. Now, when we plug in both of them into the function, the original function, d, and I'm going to rewrite this as d. Right, when you plug in these numbers into d, we end up getting 5 over 2 and 5 over 2. And so this gives us the 2 points of the graph that we were looking at, right? and we can plug it in these. Sorry. Actually, sorry, I actually had it right. We actually plugged it in into the regional function. And here my function is y, and this is, I don't want this to be confusing, but this is I'll call this g of x. So I plug it into g to come up with these numbers, because at the end of the day they were asking us to find the points on the graph that were closest to 0, 2. Now, what happened here is, if you guys notice, we're done, right? These are the closest points. But if you notice, at x equals 0, you have a relative max. What happens in this case is that if you trying to have a distance right here, right? It's gonna give us the greatest distance at x equals 0. All right, so let's move on to the next one. The next one will be finding the minimum area a rectangular page from a rectangular page is to contain 24 square inches of print, and I already have it over here, so we'll follow it from here. So our problem has a rectangular page that contains 20 square inches of print. So here's your printing, and this surface has an area of 24 square inches of print. The margins at the top of and the bottom of the page is 1.5, so here are the margins, and the margins to the left and the right, it's 1 inch. The question is, what should the dimensions of the page be so that least amount of paper is to be used? So what are we doing here? We're minimizing, right? We're minimizing the page. So dimensions be so the page has the least amount of paper. So that means you're minimizing the area of the paper, right? Minimizing the area of the paper, or the area of the page. So what I did here is I translate the problem into this picture. That way I don't have to read the problem over and over again. And if you guys notice, I did some assumptions here, right? I'm going to let A be the area of the paper, of the page, and that's what we're trying to minimize. And then I came up and say, okay, I need to figure out what are the dimensions. But in this case, I did something different though. That is not that's not as common, right? To do. Usually, we try to write this as being since we're looking for the dimensions of the page, we try that to be x, and we try this to be y. But in this case, I did something different, and I want you guys to think about this, and we'll discuss this together. Instead of making this whole thing be x, I actually made this be x, the height of the printed area. So x is the printed height, and then y is the printed width. And you guys will see that in a second, because if you guys notice now, when I'm trying to find the paper's height, the paper height will be x plus 1/2, which will give me x plus 3. And over here, when I find the paper's width, it will be y plus 1 plus 1, which will give me 2. All right, so that will give me the area, and it's very easy for me to see the area, right? Area is going to be the paper's height times the paper's width. And so that doesn't seem like I'm making anything special, but you guys will see what happens now. What happens here is that when I'm trying to describe and put this, minimize this by having this in one single variable, right? We need to have that area in one single variable. We need to use the other equation, the other information. And the other information was that the printer area was 24 square inches, which is printed height times printed width. Now in that case, I would have actually had to use x. If I would have used this to be my entire x, this would have been x minus 3, and this would be y minus 2. And this would have made it very hard for me to actually solve for one of the variables. That was the reason why I did it. Let me say it again, because at this point, if I would have gone the other way, it would have been very hard for me to solve for one of the variables. You want to keep this as simple as possible because you got to put that in here. And that's what I did, right? I had 24 equals x times y. This is my x and this is my y. This is the printed area. Is equal to 24. I'll divide both sides by x. And then now I have y by itself. I'll put it back in here. And then everything is much simpler, right? I'll distribute everything that I have, right? X times 24 over x gives me 24. X times 2 gives me 2x. 3 times 24 over x gives me 72 over x. And then 3 times 2 gives me 6. Simplify 6 by 24 gives me 30. And that gives me the area of the page. Now we have to discuss the domain of the area. So this will be a good moment for us to work on that. Obviously, x, just like the previous problem, is between x is greater or equal to 0, and the area needs to be greater than 0, right? So if x needs to be greater than 0, then what we're going to have here is we're going to have to make sure that this stays greater or equal to 0. So what we're going to do here is we're going to set the area greater than 0 and then argue the restrictions for this area. Well, if I multiply both sides by x, this becomes 30x, 20x squared, and then the x goes away. Now, if you notice, if I reorder this is positive, right? Because that's the x squared. But we also know that x needs to be greater than 0, so that's also positive, and that's positive. So in this argument, no matter what x is, whenever x is greater than 0 or equal to 0, this will always be greater or equal to 0. So therefore, there is no boundary, there's no upper bound for a, but there's a lower bound. All right, so now we'll find the derivative so that we can find critical numbers. Let's find the critical numbers for this. So we're going to take the derivative of this. The derivative 30 is 0. The derivative of 2x is 2. And the derivative of 72 over x is negative 72 over x squared, right? I move this to the top. Now I have x to the negative 1. And then I apply the derivative, right? Do you guys see that? Move this to the top. That gives you x to the negative 1. Then you apply the derivative, and that's how we got negative 72. And then subtract 1 from the power, so x negative 2. X to the negative 2, and that's how we got this one. So you can try that on your own. Then we're going to find the critical numbers by setting this equal to 0, or whenever this is undefined. We know that this is not going to be undefined. The only way that this is undefined is whenever the x is 0, which we know is not possible. So we can use that as a boundary, right? And then this one, we can use that, we can say that this is going to be 0 whenever the derivative is 0. And first thing is adding 72 over x squared on both sides, then do a cross multiplication that gives us 2x squared equals 72. And then we will divide both sides by 2, and that will give us x squared 36. And then we'll do x, apply the square root property. That will give us plus or minus square root of 36, which is x equals plus or minus 6. Now we know that x cannot be negative, so therefore the only case will be x equals 6. All right. Following the next line, we know that we have the boundaries between 0 and then without upper bound. So our number line suggests that we have 0 and 6, and we're gonna test only these boundaries, right? We don't care about anything on the left side of that. So what we're going to do here is, and then also, okay, so anyways, also in this case, this is not a part of the critical number because it's not part of the domain. Anyways, right, so moving on. So we have, we're going to test this region in the first derivative test, right? And we did that, and we got by plugging 1 we got negative, by plugging 7 we got positive, and so we have negative positive. That means a is decreasing from 0 to 6, and a is increasing from 6 to infinity. So we see something of this form, right? That's what's happening. Is decreasing the distance, the area is decreasing until you get to x equals 6, and that's yeah, and the area is minimizing, and then it becomes larger and larger and larger. So therefore, we have found that with this argument that at x equals 6, you will have the minimum area. And so now we have to find the other dimension when x equals 6 by plugging it back to the y. 24 over x gives us 24 over 6, which is 4, which means y equals 4. But remember, these were the printed area dimensions, not the page dimensions. So we have to go back and plug it into these, right? So that we can actually find the dimensions of the page. So the dimension of the page was x plus 3, so x equals 6. 6 plus 3 is 9 inches. And then the page width is y plus 2, so 4 plus 2 gives us 6 inches. And there you go. So we found the dimensions of the page. All right, so moving on to the next problem, we have, we're gonna minimize the length of a cable. So we have two posts, one that is 12 feet high and the other one that's 28 feet high. They stand 30 feet apart. They are to be stayed by two wires attached to a single stake running from the ground level to the top of each post. Where should the stake be placed to use the least amount of wire? So here you guys can see a picture of what we have. Now you could have chose to have the 28 feet on the left side and the 12 feet post on the right side. It doesn't really matter because the math will give you the right answer either way. So what I did here is I led the wire, so you guys see the two posts on the left side and the right side, and I connected this wire where my wire represents the red lines with X and Y, and you can see how it's being staked. Now when we're trying to minimize this length, we're going to try to minimize the sum of X and Y. So as you guys see here, you guys will see here that if I let that my distance of the wire will be denoted as W, uppercase, and where X is the wire from the small post and Y is the wire from the big post. So we're going to try to minimize this distance, right? We're going to try to find the absolute min for this. So eventually we have to find some critical numbers. So eventually we have to find the derivative of this. Now, because we have two unknowns, two variables, we're going to have to find a way to have it in one variable. And so this is where we becomes more challenging, right? I mean, a lot of this work is algebra based. So we're gonna, and you guys will see that there's only one line that it requires us to think about the calculus. So what I did here was I needed to know something. They all connect in this point, right? The connection between X and Y. That was my purpose. Is I gotta find another connection between X and Y. And that is, this is the connection right here, A, and then this is A. If this is A, then this has to be 30 minus A. I could have used another letter like B, but I'd rather to just keep it in one single variable. All right, so what I did here was I wrote the, by using Pythagorean theorem, because they're both right triangles, this gave me A squared plus 12 squared gives me X squared. 30 minus A squared plus 28 squared gives me Y squared. By simplifying this gave me 900 minus 68 plus A squared plus 884. And then after I did this, I actually took the square root on both sides. Now I didn't consider the minus part in either case because they are both lengths, and so that will give me a positive value. But then I took the square root, right? And then now we have X and Y. Now we tend to actually work very hard to either express X in terms of Y or Y in terms of X. But in this case, it actually seems more logical to actually keep them, both of them, in terms of A. It's very odd, right? It's actually very odd. We're actually using a different variable instead of the ones that we're looking for. So we're gonna replace X and Y in terms of A. Now I remind you guys that A has a boundary between 0 and 30, right? So it has some endpoints. So what we need to do is find the critical numbers that will minimize the length of those two. So what I did here is I copy and paste those two values, right? This is for x, this is for y, and I wrote it in terms of power so that we can recognize that we're going to take the derivative of this. And if you take the derivative of this, this gives us 2a over 2 times a squared plus 144 to the 1/2, and 2a minus 60 over 2 times a squared minus 60a plus 1684 to the 1/2, right? You have to use chain rule to get to here. You have to use chain rule to get to here. And then move the negative power down. The critical numbers will happen whenever this is 0 or whenever this is undefined. But please note that the denominators will never be undefined because they're always going to be positive. If you guys notice that, a squared plus 144 is always going to be positive. And even then, this one has a negative there, but it's actually going to always be positive. Even in the worst case scenario where this will be the most negative, will be whenever a is 30. But this, no matter what, because that one is going to be 30 squared and plus 1684 will still be positive. So it's always going to be positive no matter what. So there will never going to be 0. So therefore it's never going to be undefined. All right, so let's move on here and zoom into this part. So in this example, now what we're going to try to do is find whenever this is equal to 0. And what we're going to do here is if we set this equal to 0, we're going to move 1 to the other side by subtracting it to the other side, and that's what I did. I subtract this to the other side. Then I also realized that some things can be simplified, like those can cancel each other out, and I realized that this is also can be factored. We can factor 2, so we're left with a minus 30, and that would cancel that one. And then once I had that, then I use cross product. I multiply this across and multiply this across. And so I'm left with negative a minus 30 times a squared plus 144 to the 1/2. And then here we have a times the bottom part of this, which is that. And then what I did here is, since I wanted to remove these square roots, I'm going to square both sides. And we learned that in college algebra, right? And so what happened here is that this became a square. The square root here and the square cancel each other out, but this one became a square. This one's going to become a square, and the negative is going to go away, and this one got to cancel with that square. All right, and then we're going to distribute as much as we can, and then expand this. For the expansion of this, I end up doing this on the side, so you guys can see your notes, how I expanded that. I expanded this first, and then I expanded that, and that's how we got this expression. And then from there, once I had this expression, then I move everything to one side by subtracting a squared, by adding 68 cubed, by subtracting 1040 a squared, and then by subtracting this to the other side and subtracting this to the other side. So everything got canceled, everything is 0 over here, and then we're left with 640 a squared from these two, minus 8640a, minus 129,600 equals to 0. Then we realize that we can factor 320, and so that leaves those numbers much simpler for us to factor, which was 2a plus 45 times a minus 9. And by the zero factor property, this suggests that we have 2a plus 45 equals 0, which we subtract 45 and then divide by 2 gives us a equals negative 45 over 2, which cannot be used because it's not in the domain. That means we said that a cannot be negative. And then this one we have a minus 9 equals 0, which suggests that a equals 9. So this is a critical number. So what we're going to do now is, once we find the critical numbers and we have our endpoints, since we're looking for the absolute value, we're gonna plug it into the original equation, right? Because we're looking for the absolute. So plug in the endpoint a equals 0, plug in the critical number a equals 9, and plug in the endpoint a equals 30. When we plug in the 0, we get 53.04. When we plug in 9, we get 50, and when we plug in 30, we got 60.31. So make sure you guys check those numbers. And so the conclusion is that we're gonna get the minimum wire, the least wire amount of wire, whenever we have a stake at 9 feet away from where. If you guys notice, that A was in respect away from this the 12-foot post. So this is 9. So that means that the wire should stick at 9 feet from the 12-foot pole to get minimum wiring. All right, so that's it, right? So this is not easy, right? This is not easy problems. It's something we have to work on and get more experience. So please go over the notes as many times as you need. Go over the lecture notes, ask questions, and keep practicing. Continue to work hard, and every day you should be trying to do one problem or review some of the problems. Because there's a lot of material, and it's not necessarily too much of the calculus, but it's the algebra that we need to continue to practice. All right, please let me know if you have any questions. I'll see you guys next time. Thank you.